And welcome to this exercise on linear programming. In this exercise, I'll show you how a simple problem on linear programming can be solved by graphical method. So this is a minimization problem. A linear programming can have both profit maximization, for example, or cost minimization problems. So this is a problem that is a minimization problem. So let's just have a look at the problem, what the problem is. The problem is that there is a small petroleum company that owns two refineries, and refinery one cost $20,000 per day to operate, and it can produce 400 barrels of high grade oil, 300 barrels of medium grade oil, and 200 barrels of low grade oil. Refinery 2, which is newer and more modern, it costs rather $25,000 per day, and when it operates, and it produced 300 barrels of high grade oil and 400 of medium and 500 barrels of low grade oil. Given all these information, the company has orders totaling 25 barrels of high grade oil, 27,000 barrels of medium, and 30,000 barrels of low grade oil. Now, how many days should it run each of the refineries that would minimize its cost and still that would meet its orders, right? So the demand would be fulfilled and the firm would be able to minimize its cost. So this is a cost minimization problem. We can clearly see that. The first goal for any such problem would be to write and formulate the linear programming. So this is a formulation of the linear programming problem. There is a standard format for that. So this is how I have done this. There is an objective function. Objective in our case is to minimize the cost. So the cost is this. Cost is equal to this equation. What is this equation? So let's just define x as the number of days refinery 1 is run, and x1 is the number of days refinery 1 is run, and x2 is the number of days refinery 2 is run. Now, why do we call this? Because these are our control variables. We can control x1 and x2, which means that the firm can control how many number of days can this run firm refinery 1 and refinery 2. Now, x1 here is multiplied by 20,000 because that's when the firm runs refinery 1. It cost for each day it cost them $20,000. So that's refinery 1 per day cost. So this the number of days refinery 1 is run multiplied by the per day cost. So this would be the total cost associated with refinery 1, while this would be the total cost associated with refinery 2, which is equal to the total cost. So this is, in a way, the total cost is equal to the cost of refinery 1 plus the cost of refinery 2. This is our objective function. We need to simply minimize this function. However, we have some constraints given. The constraints are in this way we have formulated them and put them in a formal way. Now, what are these constraints? What I'll do is that I will provide the solution in this tab. So there is a minimization problem of graphical method, and this would be the solution. So let's go to this solution tab. These information I have created there as well, but what I have done here is that I have simply colored these constraints in different colors so that we can see this. So the first one is there are high grade oil. We have a constraint on this. So the first constraint says that there is firm 1, when it runs for a day, produces 400 barrels of high grade oil. So you see, 400 multiplied by a day, plus it produces firm 2, or refinery 2 rather, produces 300 high grade oil, 300 barrels of high grade oil. So this is 400 by firm 1, so multiply by the cost, that the per day cost, the number of days that we run refinery 1, multiply by each day it produces 400 barrels of high grade oil, plus the number of days we run refinery 2, multiply this by the number of barrels that it produces, the high grade oil. This must be at least equal to or more than 25,000 barrels. That is because the total demand for high grade oil that this firm has is 25,000 barrels, which means that the firm should run refinery 1 and refinery 2 in such a way that it would produce at least 25,000 barrels of high-grade oil. Then the same way, the firm should run refinery 1 and refinery 2 in such a way that it would be producing at least 27,000. That's because 27,000 is the medium grade oil demand. And why is this 300 multiplied by x1 plus 400 multiplied by x2? That's because 300 is the number of medium grade oil, the number of barrels of medium grade oil that firm 1 produces. So x1 is the number of days we will run refinery 1, and 400 is the second refinery, that the number of barrels that the second refinery produces. So this is this equation. The same way, in the same method, firm 1 produces 200 barrels of low grade oil, while refinery 2 produces 500 barrels of low grade oil. And x1 is the number of days that we run this, and x2 is the number of days that we run this refinery. So this means that this should be at least equal to 30,000. That means that the firm should meet at least the demand. Then there is non-negativity constraint. There are these two constraints that x1 and x2 must be at least equal to 0, which means it should be equal to 0 or more. It cannot be negative. The idea is that these control variables cannot go to negative, and that obviously makes sense logically as well. We cannot run the refineries in negative number of days. We can run the refinery 0 number of days or some positive number of days. Now, given these information, we have got three things. One is the objective function. Number 2, these constraints, constraint 1, constraint 2, and constraint 3. And then the third one is the non-negativity constraint. So this is called the formulation of a linear problem. Once we formulate the linear problem, we have to write it in a slightly different way. This is called matrix format. So we simply write this in a matrix format. So this is x1, x2. This is the constraint. This is the objective function. The objective function is this 20,000 times x1 plus 25,000 x2. So we simply write it 20,000 x1 multiplied by x1, 25,000 multiplied by x2. Now we have also written this in this way, like this, that x1 and x2 must be greater than 0 or greater than or equal to 0. So this simply meets our non-negativity constraints. Now coming back to this three main constraint, this is our main thing. So how will we write this? What we do simply is, this is 400 multiplied by x1, that's like this one, and then 300 multiplied by x2. So this is simply writing the same thing in matrix format. So 400 x1 plus 300 x2, that's this equation, and it should be greater than or equal to 25, or at least equal to 25,000. The same way we write the second constraint, 300 x1 plus 400 x2 must be equal to or greater than 27,000, and the third constraint, 200 x1 plus 500 x2, this must be at least equal to or greater than 30,000 barrels of oil, low grade oil. Right, so now our problem is pretty much ready for us to come to the solution. For the solution is very simple. Almost half of the problem in this kind of problems is formulating the problem. Once we know how to extract these information given in the task into a problem, proper formulation of the problem, then the solution becomes rather very simple. For graphical solution, what we do is simply find corner solutions. By corner solutions, we simply means that let's say, for example, we have this simple graph, for example. Let's say any graph. So this is a simple graph, for example. What we need in this is, we need, by corner solutions we mean when by corner solution here we mean that when one of the, I have already actually solved this, so I should rather do this again. So for example, by corner solution here we mean that when x1 is equal to, let's say this is x1 and this is x2, we can add this we can add these I think we can add these names to the horizontal and vertical axis somewhere here. Yeah, but anyways, continuing. Corner solution simply means that when x1 is equal to 0, what would be the value of x2? Or when x2 is equal to 0, what would be the value of x1? So let's have a look, for example. Now this is our x1 and this is our x2. What would be the value of x1 if x2 would be equal to 0? So let's just put x2 equal to 0. Then what would be the value of x1? And this simply means that if refinery 2 runs for 0 days, how many days will it take firm 1 to produce 25,000 barrels of high-grade oil? So we know that this is the equation. This is the first constraint. This one. Firm 1, it's 4x1 plus 400x1 plus 300x2, and this is equal to 25,000. If we say that x2 is equal to 0, which means that there is the 300x2 part is equal to 0, that means that the firm would run refinery 2 for 0 days. It's only running refinery 1 for some days. And how many would be those days to produce this 25,000? So this is pretty simple. We want to produce 25,000. It's this one. We want to produce 25,000 barrels of high-grade oil, and we want to produce it by running only refinery 1, which means that we can divide this by 400 because refinery 1 produces 400 in 1 day, and this would become 62.5. That means that if we run refinery 2 for 0 days, refinery 1 will be able to produce the required amount, which is 25,000 in 62.5 days. Now the same way, if we say refinery 1 is run for 0 days, refinery 2 would be able to produce this required 25,000 in 25,000 divided by 300 per day. So it would be able to produce it in 83 days. So this simply means that when we are running refinery 2 only and no refinery 1, because it can produce 300 barrels in 1 day, so 25,000 would be produced in 25,000 by 300. That would be this. Now looking at the second constraint. The second constraint is that we need to produce 27,000. So if we run second refinery for 0 days, the first refinery can produce 27,000 in 27,000 by 300 days. So this would become 90, and let's say we run now refinery 1 for 0 days. What would be the number of days that refinery 2 can produce 27,000? That would simply be 27,000 divided by 400. So this is 67.5. And now let's do again for the same thing for the third constraint. So let's say refinery 2 is run for 0 days, and refinery 1 would be able to produce the required amount of low grade of 30,000 in 30,000 divided by 200 days. So that's 150. And let's now run refinery 2 only. Perfect. So refinery 2 would be able to produce it alone in 60 days. So this is simply the explanation as I talked about. So now what we have these three constraints: constraint 1, constraint 2, constraint 3, and these constraints are very much ready now for us to graph them. So what we need to do is we need to graph all these in separate graphs, in separate lines. So select simply the first constraint, which is these 4 numbers, and go to insert, and let's select a scatter diagram, right? So when we select scatter diagram, click the first one. No, the first one won't give us any line, so let's just select insert and select some lines. So this is the line. So this simply tells us that when our x1 is equal to 62, at this point, this is x1 equal to 62 and x2 is equal to 0. Along this line, we know that x2 is equal to 0. This is x1. We can give them these. We can give these x's names. I think we can give this x1. And this would give the name to the total. So yeah, this is x1 and this is x2. Now what we have is that let's just add some more data and put the second constraint as well. So just select data, or simply right click here and we can have select data. And this is series 1. Now just simply put here another series. So this is series 2, and this would be x values. So our x values are x1 and our y values are x2. So we have got a second constraint drawn here. Now simply go to select data and add a third series, and for the third series select your x values, which is x1, and y values, which is x2 in this case. So we have got these three constraints. So very good. Now what does these constraints tell us? These constraints tells us that we can minimize our cost, which is this cost. However, we have these constraints to meet, which means that we cannot come underneath these. We need to produce a certain amount, and to produce that certain amount, we should run at least these many days. We should be able to produce. Let's say we should be able to run at least the first refinery 100 and the first refinery, for example, in this case 62 days, and in this case the third constraint is that we have to run the first refinery 150 days. So this is 150. What we have to do in these three constraints is that we have to take the most strictest constraints, because the strictest are the constraint that would apply. So for example, if we would have a constraint that we need to run refinery 150 days, and the second constraint is that we need to run refinery 100 days. So the 100 days is the stricter constraint. So the stricter constraint would apply in this case, which means that we need to produce at the outer lines. We need to produce while complying with the outer lines, which is this line and this line. So we can minimize our cost. We can minimize our cost and still comply with these constraints that were given, and we can produce still. And that producing area where we can produce is this area. So this is the area where we can produce. So this is called feasible area or feasible region. Now what we have here simply is that we need to find out which is the optimum point, right? Optimum would be the point, because the optimum point could be here, which means this is a feasible region. We can produce here, we can produce here, we can produce here, but obviously these are still these areas are way away. So the closer we are to this line, that means that the minimum the cost would be. However, we cannot come under this, because that means that we are not complying with at least one of the constraints. So we have to remain on or outside this line and still minimize our cost. So now let's have a look. For example, this outer point is 150 and 0, which means x1 is 150, and we can see that when I put my cursor there, we can see that this is 150 for x1 and 0 for x2. That's this number simply. So x1 is 150 and x2 is 0. Now what is this third point? These are corner points, right? These are corner points. So I'm simply pointing out the corner points. This is one corner point. This is another corner point, which is 0 and 83.33. This is this one. So I'll simply put this 0 and equal to 83.33, right? The third one is, I'll simply put them in center so that we all see this the same way. So the third point is this point. Do you see this point? This point, let me just make this a little larger. This point is also one corner, and this is 50 for x2. This is 50 for x2 and 25 for x1. So I'll just put here 25 and 50. Very good. Now what we are going, these are x1 and x2, and we need to find the cost with this. So how does the cost work? For example, we know that the cost function is like this. The objective cost function is like this. Let me just make this a little larger. So the cost function is 20,000 multiplied by x1 plus 25,000 multiplied by x2. So this is, I'll write it here, 20,000 multiplied by x1. Now x1 here is this, the number of days, 150, plus 25,000 multiplied by the number of days that refinery 2 is run, which is 0 in this case. So we will have, so this is the total cost for us to meet all these requirements and produce at this point would be $3 million, right? Because each day it is costing us $20,000 and we are running it for 150 days, the first refinery, and 0 days the second refinery. But if we run at this point, which means that we want to run only a second refinery for 83.3 days and refinery 1 for 0 days, then we would have 25,000 multiplied by, sorry, that was 20,000 multiplied by 0 days plus 25,000 multiplied by 83.3 days. Okay, there is a plus here. So that's that is 2.08 million. Now the third one is, we have, or simply what we can do is that we can draw this down and the formula will apply to this as well. However, we can again do this 20,000 multiplied by 25 days of x1 or first refinery plus 25,000 multiplied by the second refinery, number of days the second refinery is run. So this is $1.75 million, which means that this is the lowest cost, right? This is the lowest cost. So this is actually our cost minimizing solution. Let me make this green. That's a good news. So this is the whole area is feasible region. We can produce at any point here, and if we do that, we will meet our requirement or constraints. We will comply with our constraints. However, our cost would be minimum at this point, which is running the first refinery for 25 days and the second refinery for 50 days. We call this optimal point. So cost minimizing decision is 25 days of x1 and 50 days of x2. And what is the optimal solution? The optimal solution is this one, that we need to run the first refinery 25 days and the second refinery 50 days, and the minimized cost would be 1 point, then minimized cost would be $1.7 million. So that's exactly our solution. We just need to write this optimal point, feasible region, x1 and x2, and that's pretty much it. Thank you very much.